My name is Janhavi Purkar, and this is my video lab report for the individual lab 1 on constant velocity. In this experiment, we'll be observing a duster moving at constant velocity without changing direction. This presentation will also include my methods in which I constructed a computational model, an observed versus a predicted position graph, both reflecting experimental data or data from the computational model, respectively. Lastly, I'll go through some of my observations and additional questions. So this lab investigates an object moving at constant velocity without changing direction, and for this to happen, the net force acting on the object, in this case the duster, must be equal to 0. Newton's first law states that unless acted upon by an external force, an object moving at constant velocity will continue to move at that velocity, and an object at rest will remain at rest. So these two laws are fundamental principles that I used in my experiment. Hence, when there is no net force acting on the object, constant velocity is achieved. So here are a few formulas reflecting Newton's first and second law. I'll be using these in the computational model to predict the object's position and velocity as a function of time. So over here you can see the velocity update formula. This helps me calculate the final velocity given initial velocity, net force, mass, and change in time. And over here is the position update formula, which helps me calculate the final position given the initial position of the object, the average velocity, and change in time. So as you can see, when the net force is equal to 0, net force divided by mass will cancel out to be 0, which multiplied by change in time will also cancel out to be 0. This gives us the zero net force formula, which is that the final velocity is equal to the initial velocity, which also means that constant velocity is achieved. So in this video I'm about to show you, I used Tracker to analyze the video of the duster moving at constant velocity. You'll see that I took the left axis to be negative and the right axis to be positive, resulting in a downward sloping graph in my position versus time graph for the duster. Here's a downward sloping position versus time graph that I was talking about. I then used some of the data from the Tracker software to make calculations for the average velocity, which is equal to the change in position of the object over the change in time, and then also took down the duster's initial position, initial velocity, and time of last observation. This will all help me in the next part of this experiment where I constructed the computational model. I used the starter code given by the lab and GlowScript to apply Newton's second law and first law in terms of code. As you can see over here, I used the data from Tracker to set the ball. In this case, the ball represents the duster. I set the initial position and the initial velocity, which was the average velocity that I calculated using data from Tracker. I didn't edit the mass as it doesn't affect velocity calculations since force net over mass cancels out to be 0. And the while loop over here, as you can see, I took t to be less than 3.202, which was the time of last observation, and the rest of the code updates the velocity and position of the object over time. As you can see over here, this is the velocity update formula, and this is the position update formula. So here are the two graphs that I obtained from my computational model. One showing the position versus time graph of the object, and one showing the velocity versus time graph. I then used the position versus time graph from the computational model and compared it with the position versus time graph of my experimental data. I obtained these graphs by plotting down the data on Google Sheets and creating a line graph. So as you can see, the data from the experimental graph and the computational graph look very familiar, but they do differ at certain values, mostly as time increases. As per my observations, this could be due to conditions such as friction, which is not reflected in the computational model. Other possibilities is an uneven surface in reality, which could also cause friction, and differences in data, as the computational model does not take this into consideration. Additionally, on Tracker, due to human error on my part, I may not have calibrated distance accurately, which could also affect the data. Velocity might not have been strictly constant, as I assumed it was by eye, and the computational model does take velocity to be strictly constant. So here are a few more additional questions. So what if the graph axes for the position versus time graph were interchanged? Well, if the axes were interchanged, then the graph would slope upwards instead of downwards like mine did. However, the other conditions would remain the same. The graph would still somewhat show a straight line, and it would just slope upwards instead of downwards. To improve accuracy, I could use an object with a lower coefficient of friction, or try to include the frictional force into the computational model. This would give me more accurate data or more similar data between my computational and experimental data. The other question for what does it mean? Is it possible for you to say how many pushes and pulls are added together to give zero net force in the case that you observed? Well, I think it would be incredibly difficult to do this. Net force is 0 in the computational model, but in reality, this wouldn't be the case. Other than friction, there could be many different forces acting on the system that we're unaware of. And even if we knew exactly which forces were acting on the system, it would be difficult to tell which force was more dominant and what net force actually was. Thanks for watching.